Chapter 12, Chemical Kinetics. This chapter is going to be all about the rates of reaction. How fast does a reaction happen? It's not going to cover how spontaneous a reaction is. It's not going to cover whether something is thermodynamically favorable. It's not going to cover percent yield, but it's going to talk about how fast a reaction happens. So our Chapter 11 table of contents, 1.1, we'll talk about reaction rates. So what happens as a reaction goes along. And then Chapter 11.2, we'll talk about rate laws. How are we going to describe that mathematically? 11.3, we'll look at the form of the rate law. There's different reaction orders, and how can we figure out which reaction order a given reaction happens to be. Then 11.4, the integrated rate law. That's going to be how we're going to use math to predict how much of a given reaction is going to go forward over a given amount of time. So after 10 minutes, how much product do I make? How much reactant is used up? 11.5 is going to cover some reaction mechanisms. So how do chemical reactions happen? What's the physics behind that? We'll look at a model for chemical kinetics in 11.6. And in 11.7, we'll look at catalysis. So what is kinetics? Kinetics is all about speed or rate of reaction. So for example, catching lizards, an ectotherm, since this guy looks very much like my pet lizard. But lizards and other cold-blooded creatures are ectotherms, or animals whose body temperature matches their environment's temperature. When a lizard's body temperature drops, the chemical reactions that occur in its body slow down, as do all chemical reactions when cooled. This causes the lizard to become lethargic and to slow down. Chemical kinetics is the study of the factors that affect the rates of chemical reaction, such as temperature. Why do you need to study kinetics? Well, time taken by medicine to improve your symptoms. So medical professionals, biologists, if you are looking at why your body gets a fever, it elevates your body temperature, and in essence, your body's repair mechanisms are going to outpace and outproduce the rate at which the virus or the bacteria is replicating in your body. So it's a competition, it's an arms race. You crank up the temperature, you've got more of a head start, you've got more concentration. We're going to see how concentration affects rate as well. The time it takes to cook a meal. So your mom's going to care about kinetics, right? You can't just say, you know what, I could cook this for 1 hour at 300 degrees, or I'm going to cook it at 1,000 degrees for 10 minutes, right? It just doesn't work that way. The design of an engine that lets efficient burning of gasoline. So engineers care about that, right? You don't want your engine to have engine knock or noise. Expiration dates on food products, like food spoilage rates. So chemists, grocers. The role of refrigerants such as chlorofluorocarbons and the degradation of the ozone layer, so geologists or environmentalists, even forensic scientists. So they have come up with techniques to basically date wine based on the amount of radioactive carbon-14 that's in there. So you're basically radiocarbon dating things. So geologists will use kinetics and carbon dating as a tool, and that's one of the things in their toolkit. So, like I said, kinetics is the study of how fast or the rate at which chemical reactions occur. So rate is going to be concentration change divided by time change. So it's going to be some change in concentration over some time in change. A reaction is slow or fast, depending on the relative strength of chemical bonds and several other factors. Chemical reactions involve a combination of bonds breaking for the reactants and bond making for new products. And this bond breaking is always going to be endothermic, and this bond making is always going to be exothermic. Reactants need to come together and collide with one another to react. So it's part of our mechanism. How does this happen? Right? We need to have some sort of collision where the different molecules of our reactants get into touch with each other and are able to undergo that chemical change. In order for us to increase the speed of reaction, we've got a couple of different levers we can pull, but that's going to basically increase the chance of collisions between reactants happening or the effectiveness of those collisions. So this is mechanistic concerns. Right? Some reactions are going to happen fast, right? Like the reaction between sodium and bromine, and some of them are going to happen slow, like the rusting of iron. They're both exothermic processes. They're both spontaneous. One is just happening at a faster rate than the other. They're both redox processes. Right? So there is some factors that influence reaction rate. So under a specific set of conditions, every reaction has its own characteristic rate, which you cannot figure out beforehand. You've got to determine that experimentally or empirically, which depends on the chemical nature of the reactants. There are 4 factors that we can control during the reaction. 1, concentration. Molecules need to collide in order to react. If I've got more molecules, because I've got a higher concentration, they're more likely to bump into each other. Physical state. Molecules have to mix to collide. So if I've got something that's in the gas phase and something that's in the solid phase versus 2 things that are in the liquid phase, well, those liquid phase molecules are free to interact with each other. That solid and that gas can only interact at the surface. Right? Temperature. They have to collide with enough energy in order to react. So there's going to be what we'll see as an energy activation barrier. So they have to have enough energy, and temperature and energy are connected to each other. And remember, this class is all about energy. The use of a catalyst was another factor. And then surface area. So that goes back to this idea that molecules need to collide to react. The larger the surface area, the more likely you are to run into another molecule. And we saw that a couple of years ago with the sugar silo explosion, where you had a lot of sugar granules that were in the air. Those had a very high surface area. It was able to react. If I remember, I'll try to do a demo in class where we're going to set steel wool on fire, right? So something like steel wool burning or sugar silo explosions or nanotechnology, those are all going to be things that relate to the surface area. And it's really just a way to get more molecules in contact with each other. Right? The larger the surface area, the faster the reaction rate. Right? And there are 2 ways we can express these rates. So we can either look at them as the rate of disappearance of the reactants. So I've got my starting material and it's getting used up. How quickly are we running out of gas in our car? Or we can look at it as the rate of appearance of the products, which is going to be an increase or a positive change. I started out with no product. After time, I get more. I'm seeing more after a longer time. I'm going to have a positive change. So my concentration would increase. So if we look at 2 different lines where we've got a reaction between A forming B, my concentration of A is going to deplete over time. I've got less and less A as I'm starting to form more and more B. As the concentration of the products goes up, the concentration of the reactants is going to go down. So very straightforward. Right? We can express this equation where A goes to B in 2 ways. We're either looking at a negative change in A, so A is decreasing with this negative sign, or has got a positive change in the concentration of B with respect to time. So B is increasing, positive sign. A is changing, but it's changing to a smaller number. It's decreasing over time. Right? So defining this reaction rate, it's the change in concentration of a reactant or product per unit time. So rate is the concentration of A at one time minus the concentration of A at an earlier time, and our change in time is just what is time 2, my later time, minus time 1, my earlier time. And we're generally going to give these concentrations in units of molarity, moles per liter, and this little delta just means a change in. So for all of those of you who are doing calculus right now, you're like, oh, I know what that guy means. So here's another example where we're looking at average reaction rate. We've got this dissolved bromine, right? And so we've got some bromine aqueous. That's what gives it this kind of orangish color. And it's undergoing a reaction with this molecule here. And we're going to form bromine aqueous ion, which is colorless, H plus, which is colorless, and CO2 gas will be evolved, right, which is going to be colorless. And so our color is going to disappear because our bromine is disappearing over time. So our concentration of bromine, because it's a reactant, will decrease over time. So we can plot this guy out. So here's another example. We've got NO2 forming nitrous oxide and oxygen. So it's a decomposition reaction. Our reactant here, the NO2, is going to form our two products, NO and O2. So we started off at T0 with just the NO2, none of our products. After 50 seconds, we notice that we've decreased the amount of reactant, and the amount of product has gone from 0 to 0.0021 in the case of the NO, and 0.0101 in the case of the O2. And the reason why these two numbers are different, as 2 to 1, is because the stoichiometry in here is 2 to 1. Okay? If we plot this out, we'll get the following curve where NO2 right here, right, this is our NO2, is decreasing over time. And then our two products are increasing, both the oxygen and the nitrous oxide. And you'll notice that the rate at which the NO, this product over here, is increasing is going to be twice that of the oxygen. Again, because of this 2 to 1 stoichiometry. Right? So looking at this, right, we can take 2 points, let's say like this point here and this point here, right? And we can calculate a time interval, delta t, of 100 seconds, and then we can measure what the corresponding change in concentration is. And what that's going to let us do, as we'll see in a second, is calculate this tangent. Right? We can do something similar over here for the NO2. So we'll take a 70-second window from this point to this point, and we'll look at how much it changes. And we can do the same thing for the oxygen appearance. So over 70 seconds, how much did it change? And again, notice that this is a 2 to 1 stoichiometry. So the NO is appearing at twice the rate as the oxygen. Right? So what we're going to do with this is we're going to calculate what's called an average rate. So the rate of reaction for the decomposition of nitrogen dioxide, the average rate at which the NO2 concentration changes over the first 50 seconds is just calculated by looking at what is my initial concentration at T0, what is my concentration 50 seconds later, and then just dividing it by my initial time and my final time, the difference between those. So 0.0079 moles per liter is where we were at after 50 seconds, and we started off at 0.01. So what's going to happen with this negative, or with this number, is that it's going to give you a negative number over here, and we're going to divide it by the difference in time, 50 seconds, and we get minus 4.2 times 10 to the minus 5 moles per liter per second, or molar per second. Since the concentration of the reactants always decreases with any time, any rate expression involving a reactant is going to include this negative sign. Right? The magnitude, right, is going to end up as the same number, but we're looking at a negative change times a negative sign. It comes out as a positive. That's going to be really confusing at first. As you practice, you will get more used to it. So our rate is going to be 4.2 times 10 to the minus 5 moles per second. The change direction is in the negative direction because we're using that up. Okay. So looking at our average rate in moles per liter of the decomposition of NO2 as a function of time, if we look at it at this first time chunk between 0 and 50, we end up with 4.2 times 10 to the minus 5. But now we go from 50 to 100. Our delta T is still the same, but we look over here at our rate, and our concentration change is going to decrease with time. So our rate is decreasing as our reaction proceeds. So it's not happening as fast. This is kind of an advantage if you're talking about batteries. So it means that batteries aren't just going to rapidly exponentially decay. It means you're going to kind of hang on for a little bit as those concentrations go. But what you can see is that our rate is changing as the reaction progresses. We can compute the instantaneous rate, and that's the value of a reaction at a particular time. So this would be the tangent. So we had our curve, we had a point and another point, and we said, okay, we can get our average rate by looking at what's dt and what's our change in concentration, and that's going to give us our average rate, right? And at that tangent, at that point, that's tangential to the curve, that is our instantaneous rate. It's obtained by computing the slope of a tangent line to the curve at that point. So, for example, for the decomposition of NO2, a tangent line is drawn at 100 seconds. The slope of that line gives the rate at t100 seconds as follows. So the slope of the tangent line is change in y divided by change in x, with a change in NO2 concentration divided by time. Okay. So the instantaneous rate is at a specific instant in time, right? It's at a slope point tangent to the line. It is going to change, so 2.96, 2.90, 1.48, it's still going to change over time. So our tangent lines are going to get shallower as we go along. We can do the same thing for the appearance of our product. So if we have a large interval in time, a large delta T, so from 100 to 600, we can do a delta T, and we can measure the corresponding change in concentration using that uppercase delta. As we make our time intervals smaller and smaller and smaller, we eventually get to a point when it becomes infinitesimally small. When our change in dt is negligible, that's when we get that slope at that line. All right, it's a little bit of calculus. I'm not going to hit you with hard calculus for this. We are going to need to do an integrated rate law, and you're like, oh, that's probably got some calculus in it. We will give you the solved versions of that so you do not have to integrate that yourself. So our instantaneous rate, we'll continue this. But our rate is going to be negative change in NO2 concentration per change in time. Therefore, our rate is going to be our negative slope of the tangent line. So minus 0.0026 moles per liter per second. So 2.4 times 10 to the minus 5 moles per liter per second. Another way to write this guy out is molar per second, or sometimes you might see moles times seconds to the minus 1. Just want you to be aware that there's different ways to write this unit out. These are all the same thing. Right. Defining reaction rates in terms of the product requires that the coefficients of the balanced equation be taken into account. So you need that BCE. You need your balanced chemical equation. If you forgot how to do that, go back to the earlier chapter in the book, relearn how to do that. You're going to need that BCE. Otherwise, all of those coefficients out in front aren't going to work. So you're going to have the wrong ones. Make sure you know how to balance a chemical equation. The stoichiometry is what's going to determine the relative rates of consumption of reactants and generation of products. So we saw that for the example we had where we had the NO2 and it was going to form 2 NOs, right? This means that we're generating NO at twice the rate that we're consuming our NO2. Okay? So when our stoichiometric ratios are not 1-to-1, the rate of reaction is going to be expressed as follows. So if we've got a given generic chemical reaction where we've got AA and BB and CC, gives us DD, right? In terms of how we're going to express this, we're going to normalize it based on whichever one is the slowest. So we're normalizing based on the slowest one. And whichever thing happens slowest, we're going to say, okay, relative to that, everything else, we need to cut its speed down so that they are equal to each other. All right? So if you've got, 1A and 2B as your stoichiometric coefficients, you're going to need to put this down here at the bottom. Why? Because let's say this guy is 10, and we'll put it in molar per second. In order for these two things to be equal, if the rate of B is really 20 molars per second in its appearance, to make that equal sign work, I'm going to need to do what? Cut this guy in half. So this part up here is twice this part over here. But to make them equal to each other, I need to take whatever is happening over on the B part and cut it down by 2. So whichever our slowest thing, that becomes our normalized one. And again, a little bit of practice, you'll figure it out pretty quick. All right? So here's an example clicker question. If the rate of reaction is 1 delta A over 3 delta T, right? And that's going to come out as 1/3 delta A over delta T, right? Which reaction is going to fit that rate equation, right? Pause the video, give yourself a second to answer. Okay, good. Let's take a look. So you should have gotten C, right? B, C, and D are all either disappearing or appearing, plus delta C, at the same rate. A is coming in 3 times as fast. So in order for this to become equal and normalize it, we're going to have to say this is our rate for A. Right? So we want our A rate to be cut in third because we've got 3 A's. Right? So let's look at summarizing our rate information. So if this was our equation, our balanced chemical equation, we have a 2-to-2-to-1 stoichiometry. So that when we produce this, we're going to end up with a minus change in our NO concentration that is equal to the negative change in our NO concentration. But this one's going up, it's increasing. And then we're going to produce twice as much oxygen. So if I wanted to write this out as a relative rate normalized to all of these things, what am I going to need to do for this? All right, I'm going to need to make this into 1/2 delta O2 over the change in time. All right, so if you need to convince yourself, put in numbers, right? 0.15, right? I'm going to generate 0.15 this. I'm going to lose 0.15 the NO2, but in order to make that equal to the 0.3 that I'm generating from the oxygen, I need to cut that down by half. So if I've got 4 phosphorus trihydrides that are going to turn into tetraphosphorus and 6 hydrogen gases, if the molecular hydrogen is formed at a rate of 0.168 molar per second, at what rate is P4 being produced? I need to look at what is my stoichiometry between here and here. So we take our slowest guy, which has a coefficient of 1. In order for it to be equal, we'll take the rate, this guy, which is 0.1 right, this guy's the 0.168 molar per second. We need to cut that down by a factor of 6, right? Which means that this one is going to be divided by a factor of 4 from its coefficient, right? So we're going to do 1/6, our change in hydrogen gas concentration is going to be giving us the rate relative to P4 formation. So we're going to do 1/6 of the 0.168. It's going to give us 0.028 molar per second. That is our rate of change for the appearance for the P4. All right, let's look at another one. Another clicker question. At a particular time during the reaction below, H2O is being consumed at a rate of 0.0084 molar per second. At what rate is CO2 being consumed? So it's asking, what's my relative rate between the water and the CO2? Right? So things you want to consider: what's the balanced chemical equation, and whether I'm a reactant or a product. All right, pause, think about it. Right. So we know that the water was disappearing at a rate of 0.0084 over here, right? And just kind of eyeballing it, you should know that, well, if I'm using this guy up twice as fast as this carbon dioxide, this guy's going to be half as much, so it'll be minus 0.0042. If you're more mathematically inclined and you want to go through that, this is the math that tells you that. Our rate change of CO2 concentration per unit time is 1/2 of the rate change of the H2O concentration as a function of time. All right, so our answer is going to be A.